See you later. All right, good. What is it? Morning. So let's see. A couple of things. Obviously, that's what you get with makeup lectures. It's always kind of pretty hard to schedule them so that you don't get overlaps. But the wonders of video technology makes it still possible to broadcast these things everywhere around. So it's cool. So let's see. What is there in just some general observations? No labs this week except the ones yesterday. Makeup labs. No homework, no new homework, but the old homework number 4 is going to be due next Monday. Let's see, no lecture on Friday, remember that. Don't show up here at 2 o'clock. Midterm is going to be at 6 p.m. I finally figured out what the problem was with the room. The person who's in charge of it turns out to be out of the office, so that's why I didn't get any responses. But I should have a room decision by probably a couple of hours from now, where the exam is going to be on Friday evening. Also, remember, review session Thursday at 5 p.m. right here. And as I mentioned on the website, think a little bit about it in advance. What are the topics that you would like to see discussed in more detail? What are the topics that you would like to have some more feedback on? And as I said, also, we're planning to go to one alt midterm, just to give you an idea what the type of questions are we're going to be posing on the midterm. Today, I'm going to wrap up buffer sizing and technology, basically chapter 5 of the book. And then, as I mentioned, we're going to do some shuffling, because I really would like to get the project started within the next week, 2 weeks or so. So we're going to swap, jump over wires. I'm going to ignore wires for a while and go right away into some logic, static CMOS logic, the more complex logic, and then we're going to talk a little bit about arithmetic, mostly adder circuitry, because that's going to be an important part of the project, that you can design and optimize an adder circuit. Actually, a bunch of them, not one, a bunch of them. So that's really what we're going to do in the next couple of weeks, really kind of, and then we're going to go back to wires later on. Okay? Cool. So that's what I just mentioned. Remember, material for the midterm is lecture 1 to 8, but if you look at lecture 8, it's not including power. It stops with performance. So anything in propagation delay analysis and all those kind of things is fair game. Okay? All right, so let's continue where we were last lecture. So there we said, okay, now we know how to analyze the performance of a inverter. But now the next question is how to optimize the sizes of the inversions or the number of inverters to use. And we take one very simple case. It looks like a simple case, but it's a very important one because it's going to come over and over again. And again, it's basically kind of the basic of everything which has to do with circuit optimization in the digital space. So the idea is that somewhere I have, oops, let me just turn that thing on. Somewhere we have a capacitor that you have to drive. And the size of that capacitor can be defined by a whole bunch of circumstances. Like, for instance, when it's a bus on a chip, you might have a whole bunch of devices connected to it. Right? You have memory connected to it. You have other register files. There might be other computational units. All of those add to a capacitive load. And then you have these long wires that go from one side of the chip to the other side. That adds to the capacitance as well. So somewhere I know I have a large capacitance to drive, and I would like to do this fast. So the challenge is how to do that in the best possible way. And as we discussed last lecture, the best way to drive a capacitor fast is obviously to use big transistors. Make them as big as possible. But then you have the problem that if I would make, let's say, this inverter really, really, really big, and I would drive this directly from a very tiny inverter in an ALU or something like that, I've just moved the problem forward because the input capacitance of those big transistors is going to be huge as well. So the next gate is going to be loaded, and so on and so forth. So you have to optimize the whole chain in one shot. So somewhere here we start with a tiny capacitor, which is your internal capacitance, let's say, in an ALU or a multiplier or an adder. Let's say of the range of a couple of femtofarads, typically. 90 nanometer technology, internal nodes have about a femtofarad capacitance. And then you have to drive this big capacitor, which could be hundreds of femtofarads, could be a picofarad. And I want to do this fast. So the question is that we're asking ourselves is how to size those inverters, number one. And two, how many should we use? How many inverters should we use in the chain? And as I mentioned last time around, the nice thing about this problem is that it's perfectly tractable. You can actually come up with the optimal solution. You know what it is. And that's quite nice. And that's what we have to derive first. But in order to derive that optimal solution, I first have to build a model. I'm going to build a model, a simple model, that allows me to write down some equations of the delay of this circuitry here and apply some optimization or some analysis on it. So the model, if you look at an inverter, the delay model is actually quite straightforward. Right? If you look at the delay of an inverter of a certain size, and the size is determined by the width of the transistors, with a certain load capacitance, we see that the delay is a linear function of the load. If I increase this capacitance CL here, I will get a linear increase in the delay. That's no surprise because we know that the delay is going to be 0.69 times the R equivalent, which is the resistance of the driver, times the load capacitance. So if I increase the load capacitance, which is the sum of this intrinsic capacitance and the external capacitance, if I increase that external capacitance, my delay goes up linearly. And if I have no load, then the delay is only going to be due to the intrinsic capacitance, this diffusion cap that sits at the output of my node. And that's this delay here for zero load. Okay? So we can easily capture that in an equation, a very simple equation. And actually, the beauty of the equation we're going to go after is rather than this intrinsic capacitance is kind of a nasty parameter. It's an internal parameter that kind of sits in between. What I would like to do is express the delay as a function of what I see as the input capacitance, because that's going to determine the load for the previous stage, and the load capacitance CL, which is the load of the next stage. If I can do that and use only those parameters, I can start chaining things together in a very methodological fashion. Okay? So let's play around with this equation. And you, straightforwardly, as we said, the delay is equal to the resistance times the intrinsic capacitance plus the load capacitance. And then we're going to do some manipulations on this equation. We're actually going to try to get rid, put it as a function of the ratio on one side of CL and Cin, where Cin is this capacitance that I see looking into the inverter. I look at my inverter and I see the gate capacitance offered by that inverter. That's Cin. And I have my load capacitance CL. And the ratio between those two we call the fan out. It's kind of the transformation ratio of that inversion. It has an input capacitance Cin, and it drives an output capacitance CL. Okay? So we just call this F, that ratio. And then we can say that the propagation delay of this inverter is going to be equal to a couple of factors. First of all, one parameter T invert, which is, if you look at it, it has as units time. It's the delay of an inverter. It's an intrinsic delay of the inverter without any load. Okay? So, and we can easily derive the equation, as you can see here, is 3 times ln2, 0.69. 3 because 1 plus 2, 1 for the NMOS, 2 for the PMOS. L times R squared of the equivalent resistance of the device times the gate capacitance, which is CG is the capacitance of the gate per unit area, or per unit width. As you can see, this is not a function of the width whatsoever. The invert is an intrinsic technology parameter. So if I now make a big inverter or a small inverter, the T invert is the same value. Okay, that's an important one to observe. And then my propagation delay is going to be this T invert, this intrinsic technology parameters, times a parameter gamma. And gamma is also a technology parameter. It's really the ratio of Cint over Cin. Or it's the ratio, if you look again, Cint is this diffusion capacitance, Cin is the gate capacitance. You can imagine that this is, again, a pure function of technology. It depends on, you look at a particular technology, you compute the diffusion capacitors, the sidewall capacitance, the bottom plate capacitance, all this type of thing, and you get a certain value. And on the other side, the gate capacitance is given by the gate oxide. Right? If I make my inverter bigger, I will basically increase both the gate region as well as the drain and source regions. So as a result of that, there's a fixed ratio in some sense, if I use the same topology, between the diffusion cap and the gate capacitance of an inverter. Okay? So that's that gamma factor. And the beauty of it is that it's approximately equal to 1. If I look at most of the inverters I'm playing around with, and you compute the diffusion cap, and you compute the gate cap, and you see it's close to 1. It might be 1.2, 1.3, whatever. But it's close to 1 for most technologies. Okay? So, bottom line is now I have a very simple equation of my propagation delay of a gate. It's a function of technology parameters, TP invert times gamma, and then something which is a factor of the ratio between the gate capacitance and the load capacitance. The load capacitance is something I don't determine. The gate capacitance is obviously a function of the size of my inverter. If I make my inverter bigger, my gate capacitance will go up and my F ratio will go down. Okay? Okay, we have that equation. Now, let's go to the next step. Suppose now that I'm saying, well, gee, I'm going to make my problem a little bit simpler. Just let's say that I assume that I have n inverters between my input and the output, load capacitance. N being any number, fixed number, 2, 4, whatever it is. Okay? So now I'm going to try to figure out is how should I size those n inverters in such a way that I minimize the propagation delay between in and out. Okay? So the beauty of propagation delays, as we discussed before, is that this is an additive property. If I have n gates in a row, the delay of the n gates in a row is the first gate plus the second gate, the third gate. I just add up the propagation delays. And that's the total propagation delay of this chain. So TP is just TP1 plus TP2 plus TPn. Now I can use my equation for each of those gates, my propagation delay, let's say the propagation delay of gate TPJ is the jth inverter in the chain, is going to be equal to T invert, again, constant, plus gamma times gamma, plus the ratio of the load capacitance, which is the input capacitance of the next inverter, and its input gate capacitance. So it's the ratio of C in J plus 1 over C in J. Okay? And I can do this, I just add all those things together, and I get an expression of this type. So the propagation delay is T invert, constant, plus the sum over those gamma, plus those ratios of my input capacitance to output capacitance of every inverter. There's two extra constraints we have. We say that the input capacitance has to be a certain value. Let's say I'm going to make, for instance, the first inverter minimum size. Because I want to make sure that the load on the previous state is fixed. Okay? Anything that sits in front of here should see a fixed load. So we make this size 1. Whatever size 1 means, but this could be, for instance, be minimum size inverter. So we know the input capacitance Cin of gate number 1. The other thing we know is the load capacitance of the last stage is a given factor 2. That's my big capacitor CL that I want to drive. So we know that Cin n plus 1 is equal to CL, and we know that Cin 1 is going to be equal to C min, let's say the minimum input gate capacitance. So those are given. Okay? So my goal now is to figure out how should I size those different capacitors, or in other words, how should I size the gates in such a way that TP is minimized. Now we have an expression. Once I have an expression, I can start playing around with this. Well, the way you do this is, if you look at it, this has a number of parameters. And the parameters are basically the sizes of your n gates, which actually n minus 1 gates, because this one is given. It's minimum, it's 1. So I have n minus 1 parameters that I want to optimize. If I want to minimize for those n minus 1 parameters, how would I do that? Well, I take the partial derivative of Tp with respect to each of those sizes and set it to 0. Right? So I write down a number of partial differential equations. Okay? We do that. We say, okay, here's your Tp, and we set the partial, the differential of Tp with every one of those capacitance equal to 0. And you can easily compute every one of those. Actually, the expression is very simple. It's very straightforward. Now, question is, what's the answer? If I now have those equations, what's the result? And the result is actually amazingly simple. What it says is very simple. If you take all those partial differential equations, you write them down. You write down all those equations here. You see T invert drops out. What I see is that 1 over C in J minus 1 minus the input capacitance. So you have the previous input gate capacitance. You have the input of the next gate, and you have C in squared. If I rewrite this, I can say that C in J squared is equal to C in J plus 1 times C in J minus 1. Right? And that's just the same expression. I can write this down for every one of my stages. What it says is that the input capacitance of state J should be the arithmetic average between the input capacitance of the previous gate and the next gates. Arithmetic average is the square root out of those two values. Okay? Geometric, sorry. Thank you. Thank you. You're right. It's the geometric average between the two. Now, again, I can write this down even more extremely. This is the same thing. If I reorganize, this is the geometric average, and thank you, it was on the next slide. That's where you probably got it. So geometric average between the two previous stage, next stage. But I also can rewrite this. It says that if you look here, C in J over C in J minus 1, that's the fan out of stage J minus 1. This is the fan out of stage J. It's the output capacitance over its input capacitance. And if I do this over all stages, what I get is that the fan out factor F of every stage should be identical. So every stage will have exactly the same, or should have exactly the same ratio between its input capacitance and its output capacitance. So that's beautiful. Because remember now, and actually it's a logical answer, right? Think about it. If I have a bunch of gates in a row, and I want to minimize the overall delay of that whole structure, what do you think is going to be the optimal solution? Do you think it's going to be better to have one stage carry most of the propagation delay and the other ones taking less? No. Actually, what you would like to do, and that's true with most of the optimization problem, you have a chain of things. What you're going to do is make each of them work exactly even the same as hard as the other ones. Or in other words, you're going to divide the propagation delay equally over all stages. Every stage will provide exactly the same amount of delay. That's typically what you see in an optimum solution. So every stage has the same delay. And that's true, right? If you know, if the fan-out factor f is constant, remember, Tp, the propagation delay of the stage, is going to be equal to gamma plus f. So gamma is a technology parameter. You have your T invert here, which is another technology. If I make f the same for every stage will have exactly the same propagation delay, right? So what does that now mean? If I make f equal for every stage, well, we can say that now every stage has the same f. But the question is, what is f? What is the value of that fan-out factor? Well, we know. Because we know that the total fan-out between the first stage and the last stage, that's known. We know the input capacitance, that minimum gate capacitance. We know the output capacitance, CL. So we have a factor called capital F, which is the ratio between the output capacitance of this whole chain and its input capacitance at the input, F. And you have n stages in between, each of them basically providing a fan-out with a factor F. So you have first stage factor F, you put it all together, we see that the ratio between CL and Cn is going to be equal to this optimal F to the power n stages in a row, right? First factor has a factor F, the fan-out of the first two stages is going to be F squared, F to the third, F to the fourth, F to the nth. And F to the nth has to be equal to capital F. Yes?
How do you select n?
N is, good question. I'm right now solving a simplified problem. I say, okay, assume that I pick 5 or 3. In the next thing, then I'm going to relax on that. I say, okay, what's the optimal n? But right now, let's assume that I pick a value n. Let's say 4. Okay? So then the effective fan-out of every stage, if you have f to the nth is equal to capital F, well, then we can compute f by just taking the nth root out of capital F. So for instance, let me take a very simple example. Suppose that I have a ratio capital F equal to 1,000. Okay? Means somewhere I have a capacitance, input capacitance of 1 femtofarad, and I'm trying to drive a capacitance of 1 picofarad. And let's assume that I'm going to use 3 stages between the input and the output. Let's say 3 inversions. So small f in that case is going to be the third order root out of 1,000, which is equal to 10. So what we're going to do is going to make every inverter a factor 10 bigger than the previous one. So the first one is 1. Second one is 10 times larger, it's 10. The third one is going to be 100 in size. And that's going to drive a capacitance which is 1,000 times larger. You see this very gradual sizing up of the inversions in such a way that each of them provides exactly the same amount of propagation delay. Okay? So if you know that, then we can easily compute Tp. The absolute minimum delay, given n, is going to be the capital N times T invert times gamma plus the nth root out of capital F, or this small f. Okay? So this will be 10 plus 1 is 11 times T invert times 3, which is the number of inversions in this particular example. So you get 3 times T invert times 1 plus 10 is 11. It's 33 times T invert, approximately. And you can show that if I would pick only 3 inversions, this is the absolute minimum delay I can get with this technology. You cannot go faster with 3 inversions. This is the absolute minimum. Okay? Now, the question is this ratio 10 a good number? Right? That's the next question you have to ask yourself. Is this reasonable or not? So we'll come back to that in a minute. But again, let me show you the example here. Same deal. Let's suppose that CL is 8 times C1. In that case, we have, again, 3 stages. First one is 1, F squared, and F is the third root out of 8 is 2. Okay? Same deal, like we did with my factor 1,000. So that's good. But I have still punted on the problem, as you said. Basically, I punted on the problem, how many inverters should I use? Should I use 3, 5, 10? God knows, right? So we're going to make it a little bit harder. We have solved the first problem. Now we can go to the second one. So we are given the size of the first inverter, which is minimum size, let's say, and the size of the load that needs to be driven. And now we want to find not only the sizes of the gates, but also the number of gates that I would like to insert in between the two. Okay? So we have to find n, the value of n, that minimizes this propagation delay equation. And this factor here, as we said, is capital F. Okay? So that's what we try to figure out. What's n that minimizes this number? Okay. We can just rewrite the equations a little bit if you know that f to the n is equal to CL over Cn. We can take the log of that, and you can find n as a function of ln f, and whatever it basically is. So we can write down our propagation delay, and we have this expression where propagation delay is basically only a function of small f, right? That's the only parameter I have. I have to determine what is small f that's going to minimize the overall propagation delay. And if I know that, then if I know small f and I know capital F, because n is equal to capital ln f over ln f, I know n, right? So if I know what the optimal, absolutely optimal value of small f is, I'm done. I know exactly how many stages I would need. So how do we do that? We take our propagation delay and take the derivative with respect to small f. I already assumed here, the reason I assumed that all stages have the same fan out, right? That's what I assumed, that this is going to be part of my optimal solution. So I take that whole derivative and I play around with it, and I get this kind of nasty expression. And actually, the answer is shown right here. It's an implicit equation, unfortunately. It's not something where I have an explicit result for. F is the exponential of 1 plus gamma over f. So I cannot really take f out of there and come up with an explicit equation, unfortunately. So we have to solve it using MATLAB, or whatever it is. You take the equation and you say, okay, given gamma, because that's the only parameter that's left in here, given gamma, what's the value of optimal value of f? And you can easily solve that. You throw it in MATLAB, and it comes up with a very nice solution for that. However, there's one case where actually this thing collapses and becomes actually quite easy to solve. When I put gamma is equal to 0, let's assume that all your load capacitance is basically coming from the fan out. And we assume that the intrinsic capacitance, this diffusion capacitance, is ignorable. Then gamma would be 0, right? If I would have no diffusion cap, gamma would be 0. Okay? If you put gamma 0 in here, you basically get fx exponential of 1. We know that number. It's E, right? And E is 2.7881, you know, the standard number. So the optimal number, if you wouldn't have diffusion thing, basically what it says is, what we should do is size up every inverter with respect to the next one, just like the factor with the factor E. 2.7. You make every stage 2.7 times larger than the previous one. And you'll get the optimum solution. And the number of stages that you have then, since ln f is 1, this factor becomes equal to 0. That basically, if f is, if f is equal to E, this is equal to 1, n is nothing else than, or the number of stages is the natural logarithm of my large fan-out factor f. Okay? That's what is written here. So out of there, we have the number of stages. This is a famous result. It was written for the first time, I think. It was published in a book in 1979, a very famous book by Mead and Conway. Carver Mead, a very famous person in the electronics industry. He was a faculty member at Caltech. And he was one of the first ones to say, well, chip design should become like computer programming. You should make it structured, you should make it organized, and all this kind of thing. So he really he was kind of at the beginning of what people called VLSI, very large scale integration and structured design. So in there, they basically published this result, and they called this the exponential horn. You can see that if you want to drive a capacitor, what you do is you kind of make your small inverter and a bigger inverter and a bigger inverter and a bigger inverter and a bigger inverter, and the sizing factor between them is just equal to E. That's why they call it an exponential horn. Okay? Now, unfortunately, gamma is never equal to 0. So it's not going to be as good. It's not going to be 2.7, unfortunately. I like nice, simple answers. This is simple, but unfortunately, it's too simple. So what I'm going to do instead is say, well, gee, no problem. I can solve the thing with MATLAB. And that's exactly what it plops here. It basically is the same equation. F is equal to the exponential of 1 plus gamma over f. And I plot this as a function of gamma. Okay? So when gamma is equal to 0, I get E, as we would expect. Now, as I mentioned also, gamma is typically around 1, or a little bit larger than 1 for most technologies. So if I plug that in here, it shows that the optimal number, F optimal, is equal to 3.6. So you make every stage not 2.7 times larger, but 3.6 times larger. Now that's a hard number to remember. 3.6. Designers are kind of simplistic people. They say, well, it's a little bit too hard. Actually, why not make it 4? Actually, I'll show you in the next slide that it doesn't really matter that much. You don't make it 3.6 or 4. The difference is going to be very, very small between the two. And that's a very famous number because it says if you want to optimally size a chain of gates for minimum delay, what you have to make sure is that every gate drives 4 gates. The optimal fan-out is 4. And remember way back when we talked about propagation delay analysis, that typically we're always going to use a load of 4 for inverter. That's where it comes from. It is the optimal number. It is what is going to minimize your overall propagation delay. Actually, this shows the same deal, but it plots now delay as a function of small f. And as you can see, if gamma is equal to 0, that's no intrinsic capacitance. We see the optimum value is approximately right here, that minimized delay 2.7. If, however, we take gamma equal to 1, you see here, optimum value is about 3.6. But you also can observe that the minimum is very flat. It's not a very steep curve. It's a very flat type of distribution. So that's what really matters. If I take 4 or 3.6, the difference in delay is going to be very minor. And that's why we say, okay, stick to 4. Don't make it 3.6. It's a lot easier. Just size everything up with a factor of 4, and you're going to be perfectly in good shape from a performance perspective. And once I know that, then I can compute exactly how many stages I need, right? Because I have that equation right here, where capital N is the ratio of the natural logarithm over capital F, which is your large fan-out, times ln divided by ln4. And that gives me the number of stages. And that gives us a perfect, clean, nice answer to how to optimize an inverter chain. Okay? This is a very important result because it actually not only is going to work for inversions, but later on we'll basically expand it also if I would have, let's say, complex gates like NAND gates, NOR gates, XOR gates, and/or invert gates, all those type of things. Because you have these very complex logic functionality blocks. How should I size the gates? Such a way that I get minimum delay. We're going to fall back to similar type of mechanisms to analyze that. Okay? Now, it's interesting to see how much impact you have by using this optimal sizing. And I just show some very simple examples here. Suppose that I have to drive a capital F which is equal to 10. So it means my input capacitance ratio to the output capacitance is 10. Question is, how many stages should I use for the optimal delay? And what is going to be your optimum delay for that particular case? So if I would take no buffers, so I just take a minimum inverter driving that capacitor which is 10 times larger. then we know that the propagation delay is going to be 1 plus 10, because f is 10 of that stage, so it's 11 times t invert. Okay? So the unbuffered delay in this case will be 11 times that t invert factor. Okay? And there's only one stage. If I now put 2 stages in there, turns out that in that case, you figure out exactly how to size your different gates. We see that the delay goes down from 11 to 8.3. So it's smaller. 2 inverters is actually going to be better than a single inverter in this particular case. And actually, if you would find the optimal number of stages, the answer is going to be 2. Not 3. By the way, you always have to have an integer number of inverters. Sometimes you might end up with 3.7 or something like that. Then you have to round it upwards or round it to somewhere a closer integer number. I cannot have half inverters or quarter inverters, unfortunately. So in this case, 2 inverters is the optimal solution. But now you can see if I start increasing capital F, like if I would just, let's say, factor 10,000, we see that the unbuffered delay will be 10,001. That would be huge. It will be an enormous delay. If I have a very tiny inverter driving that huge capacitor, it's going to take forever. If I take 2 stages, just adding 1 extra inverter already goes down from 10,000 to 202. That's a reduction by a factor of 50 in delay by just adding 1 inverter in between there. But actually it turns out that if you would have the total optimal number, which is in this case you use a factor of 4 for every stage, so you can figure out exactly how many stages you need, we see you can go down to 33. Absolute minimum delay. You cannot go any faster than that. Or the only way to do it would basically to have a better technology. Right? This is for this technology. That's what I'm going to get. That's the best thing I can do. Is 33.1 times T invert. Okay? So this is the same deal. It shows the same thing. And basically, suppose I have capacitance of 64. 1 stage gives me a delay of 65. 2 stages give me 18. 3 stages gives me 15. And then I put 4 stages. I'm starting to overdo it. I have too many stages. Delay is going to go back up. You pass the optimum, and you can see it goes back up to 15.3. So in this case, 3 stages is the optimal solution. Okay? All right. Now, that's the beauty, that's the ideal answer. Okay? So I can give you an answer which gives you the absolute minimum delay. I want to put one caveat, however, on this thing. And the caveat is that minimum delay does not come for free. It comes with a cost. Anytime when I go really fast, I'm going to have to pay for it. Actually, the best way to look at it would be to say, well, gee, I can plot my delay. Somewhere here, let's say, let me put delay. Let me see if I have a curve here. This is energy, and this is delay. So if I want to get to the absolute minimum delay, you want to be somewhere up here, I can do that by this optimal sized inverter. Okay? But in reality, there's a whole bunch of different solutions in this space. And you can see that the minimum delay always comes with an overhead. In this case, it's energy. I'm paying for it in area, because obviously I'm going to need this the last stage is going to be big, right? You have this big capacitor, you have big transistors driving it. That's going to take you a lot of area, but also a lot of capacitance. Because if I have this gate capacitance of this inverter, also has to flip up and down and up and down and up and down. So it's going to add area, and it's going to add power dissipation. So if I have this big chain here, and I want to figure out what's the overall capacitance, well, you have your load capacitance. That's a given. I cannot change that. I have my input capacitance. I cannot change that. But you can see that all those extra capacitors here is overhead. What I'm doing is adding extra capacitance to drive this load capacitance as fast as possible. right? And you can easily figure out what the value would be. It's Cin plus 1 plus f to the n. Now, f to the n, that's my load capacity. That's given, so I can take it out. So we have the input capacitance given. That is given. So we get a factor here which is equal to f times f to the power n minus 1 over f minus this nice little expression here. That's extra capacitance I'm adding in the design to go fast. Okay? So I pay for that in terms of power, because you have to multiply this CL times VDD squared. Every time I'm basically going to change this. This one is going to go down, this one is going to go up, this one is going to go down, this one is going to go up. So extra power dissipation. Okay? So it's actually, the numbers can be quite high. For instance, if I want to drive a capacitor of 20 picofarad, okay? And I assume, let's say, that the input capacitance is 50 femtofarad. So the ratio between those is approximately, we can know the ratio, we can compute the optimal n using our factor 4 scaling factor, right? So n in this case would be 6 stages. It says use 6 inversion stages. You compute that capacitor value here. So the load capacity is 20 picofarad. In order to drive that, we add another 11.6 picofarad of internal capacitance. Or in other words, I add another 50% of power dissipation to do so. Okay? So for some people, that's okay. Some people are happy about that. It's okay, I want to be fast. I don't care. I want to be here. In my energy delay curve, I want to be at the fastest possible place you want to be. But often you say, well, gee, is it really necessary for me to be as fast as I can? Sometimes, let's say, I'm backing off from the minimum delay, and I back off, let's say, 10%. 10% backing off from that, actually, from that minimum delay, actually can reduce energy by quite a huge number. Instead of needing 6 stages, I might fall back to 4 stages, for instance, and reduce that internal capacity substantially. And that's where the art of design comes in. You know, I can design something for the fastest possible delay, or on the other side, I could design something for the minimum energy, but then you're going to be extremely slow. As you can see, if I minimize my energy as much as possible, I'm going to be here. You see that I'm going to be extremely slow. The delay is going to be huge. So you can design for the extremes, and we know where to be at, but very often a good designer says, no, 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 no. What we're going to do is just back off a little bit. It's okay for me to be 5% slower than optimum speed, or 5% away from the minimum energy, if it helps me to regain a lot of performance or power efficiency. Okay? So that's an important game we're going to play, and that's going to something we do later on when we are going the project. That's kind of the game we're going to play. And say, you can go for minimum delay, for instance, but maybe it's better to back off a little bit and optimize energy and delay maybe simultaneously. Okay? Good. So this is kind of just summarizing what I just said. It shows you kind of the overhead capacitance and delay. So the blue curve is capacitance. The black curve is, this is my propagation delay as a function of number of stages. So you can see I have, let's say, 20 picofarad load capacitance and 50 femtofarad Cin. If I take too few stages, I have very small capacitance, but the delay is huge. Then I go to 3 stages, delay goes down, the capacitance goes up, and so on and so forth. At 6 stages, I get the optimum value. Obviously, doing more stages than necessary is always a stupid idea. It doesn't help you for anything, right? I put more and more inverters in between there. Your delay goes up and your capacity goes up. So you don't want to be here. Like on the right side here, that's really bad design. I won't give you a very good grade if your project ends up somewhere up here. You want to be on this side. But that's where the trade-off game, right? You see delay goes down, capacitance goes up. And I can trade off the two with respect to each other. Okay? All right. So that's basically the whole story about our first sizing optimization problem. And as I said, it's nice because it's a very tractable problem, very nicely optimizable, nice answers. You know, it's not always as easy in life. This is one of the easier cases on how to come up with an optimum design. Okay? All right, so what I'm going to do in the last half hour is wrap up on Chapter 5. And I want to say a couple of things about something which is called technology scaling, or looking at the impact of technology scaling. Okay? So we have derived a set of equations for power. We've taken an inverter. We've derived the equations for propagation delay, power density, all those energy. We know all those numbers now. So you might always ask the question, and people have done for a long time, say, now, suppose I am, let's say, at 130 nanometers. Okay? Now I go to 90 nanometers. What is that going to do to my propagation delay? What is it going to do to my energy? Will it go down? Will it go up? By how much will it go down? And so on and so forth. This is what's called scaling theory. It's trying to predict what's going to happen with delay, or energy, or power, when we go from one technology node to the next one, to the next one, to the next one. Very important for the industry, because, and also area, obviously. It's not only power, and so it's TP, it is P, it's energy, and area. Obviously, these are the numbers you're looking at. Now, this is very important, because I'm a company like Intel, IBM, or something like that. I say, okay, I'm going to go for 32 nanometers. I'm going to plunk down $8 billion just to set up a fab. It's not a sizable number. You better know in advance what is going to help you. If I basically put $8 billion down, I better know if it's going to be good for anything. If it's going to improve my propagation delay, by how much. If it's going to reduce power, it's going to reduce the cost of my transistors. Right? These are important questions to answer. So actually, the semiconductor industry, which is a fairly decent industry, it's about, what is it? Per year, Intel is about $40, $50 billion. Take all the other ones together. That's a $100 billion industry per year. Not bad in terms of overall revenue. That's a decent number to start with. Okay? But remember, $100 billion, and you take $8 billion to build a new fab, that's a sizable chunk of your whole industry. So you better think twice before you basically plunk all that money down. As a result of that, there's the semiconductor industry, since the early 1990s, has a set of committees, people that are supposedly smart, getting together and kind of trying to predict the crystal ball. They say, what's going to happen 5 years from now? What's going to be the propagation delay 10 years from now, 20 years from now? And make a lot of tables that kind of predict where the technology is going to go over the years to go. So that I can predict today that a microprocessor might be taking 115 watt or 200 watt a couple of years from now. So this committee is called the ITRS, the International Technology Roadmap for Semiconductors. And it's a bunch of Excel sheets. It's the bottom line. It's basically a whole bunch of tables, and they put equations down, and they say, well, if my transistor gets a little bit smaller, capacitor is going to go this way, the interconnect capacitor is going to go with that, the supply voltage is going to scale by so much, the threshold is going to be approximately like that. You plug it all in there, and you get a prediction of what your delay or energy could be at. This is a very interesting document. It's published, it's renewed every 2 years, and it's available on the web. If you go to you go to Google and you do ITRS, you'll find it. It's a fairly hefty document with a lot of nice charts and a lot of tables in there. But it's very useful because people in the industry use this as a guide mark for themselves to basically determine how to make investments, what they could build. They say, well, can I build a cell phone that can do this 4 years from now? Or should I go to a different technology node? So decisions like that are made based on those predictions. Very interesting type thing. Now, The bottom line is still that technology scaling, let me summarize what the latest table says. It goes till about 2020, the latest predictions, which is what, 12 years from now? 2020, they predict that transistors might be around 12 nanometers in channel length by that time, and so on and so forth. So there's a whole bunch of predictions there. Now, there's also a whole bunch of red flags. It says, we want to design those things with 12 nanometers, but there's a bunch of problems that we still haven't solved yet. There's still a bunch of problems that need to be solved before we really can get there. So they basically flag important areas for research in that roadmap. But the bottom line is that for the next 12 years, the prediction is that we will, at least a bunch of companies, like Intel, IBM, Samsung, TSMC probably, will probably keep on pushing on that technology scaling roadmap. Right now, 65 nanometers, 45 nanometers next, 32, 22, 18, 12. That's kind of where the different feature sizes will be seeing over the years here. Okay. And the main reason they still believe that it's worthwhile doing these things, even though the cost of building a fab like that is going to be humongous, is that the following thing. We still want to make electronics cheaper. That's the whole idea. You either want to get more function for the same money. Like, think about it, your laptop hasn't gone up in price. Typically, it's been, depending on what type of laptop you're taking, is $1,500 to $2,000. The cheaper one's $600. So microprocessor cost has been constant. But every generation, you get more computational power. Or the same thing with the cell phone. Cell phones haven't changed that much, except obviously you have things like the iPhone, which go exponentially more expensive because they have a better cover or better user interface or something. But it's not because of the electronics. So the cost of the electronics is basically a constant factor, while you're getting new stuff all the time. So that's one thing. So you get more functions for the same money, or the same function becomes cheaper all the time. And at some point in time, it becomes ignorable. You don't even think about it anymore, right? So bottom line is, price of the transistor is going down from generation to generation. And so as long as this is true, we will keep on scaling technology. As long as I can make something cheaper by using smaller feature sizes, we'll keep on doing it. If, however, at some point in time it becomes more expensive to scale further, then some people will scratch their hair a little bit, say, what the heck are we doing here? And in some areas, companies already start doing that. Like, say, for mixed signal design, analog design, some companies says, well, do I really get a lot of value going to 65 nanometers? Actually, if I want to do analog design like it was in 240 here, there's companies like Analog Devices, National, well, we're happy with 90 nanometers. We're not going to scale to 65. While on the other hand, you have companies like the digital guys, they're still hung-go, right? We want to get smaller, we want to get more transistors, and so on and so forth. So, but it's an interesting question, right? And while you're doing so you're getting cheaper, you also want to make it faster, smaller, lower power, and so on and so forth. So, now the question you have to ask yourself is, how do we make those predictive tables? Right? This ITRS, what's the basics of it? And what I'm going to tell you a little bit is going to be a little bit simplistic right now. But it's actually not bad at all. Actually, it gives you a fairly first-order shot at trying to predict what's going to happen with delay. Actually, the first person who observed this thing, that actually was not that hard to predict things, was Dennard. Dennard is one of those other kind of landmark figures in our industry. He's still working at IBM Watson. He must be close to 80, I think, or something like that. But you go to a seminar, you give a seminar at IBM Watson, Dennard is always going to be sitting in the first row. He's always there. He always asks questions, things like that. So he's still a very active person, very bright person. So he invented this idea of Dennard scaling. Well, he invented scaling, and then they called it Dennard scaling afterwards. So that was in 1974. He basically came up with this rule. It says, from technology to technology node, we're going to scale things by 30%. Okay? So if you look at the feature sizes, we go from 130, we go at the 180, 130, 90, 65, 45. You look at the ratio here, the ratio is 0.7. Right? Every time we scale down things with a factor of 0.7. Now, why 0.7? Why is that an interesting number? Well, it's actually the more interesting number is when you square it. When you square 0.7, what do you get? 0.49. So what basically happens is that every chip gets 50% smaller. It's squared, right? So you have one dimension here. You scale it by 0.7 in size. 0.7 on the other side means that the same functionality scales. The area of a chip scales with a factor of 2 from generation to generation. Okay? That's what that 0.7 factor does. Or if you think about it, if you put the same functionality on that chip, it means that we double transistor density from generation to generation. The number of transistors per unit area goes up with a factor of 2 from generation to generation. Okay? What else do we get? And I'll prove that in a second. If I scale things down with 30% in dimensions, it turns out that the delay also goes on approximately as the feature size. So your propagation delay of your transistors or your inverters goes down with the factors, goes down to 0.7 approximately of the previous generation. Now, 1 over delay is what? That's frequency. If you do 1 over delay, it turns out that you do this number, you see that the frequency goes up with a factor of 43% as a result of that. That was the good old days, by the way. Right, we'll come back to later and say, well, maybe some of those things aren't. One second. So let me just turn this thing off. Good. So the frequency goes up with 43%. If you think about it, it's 1 over this 0.7. Okay? The energy per transition, if we assume, and I'll come back to that in a second, if you assume that not only the feature sizes scale, but we also scale the supply voltage. While we're going down in feature size, we're going to have to make your supply voltages smaller as well. It turns out the energy per transition would go down with 65%. Or if you, that's 50% power savings at a 43% increase in frequency. Okay, that's the ideal model. So this is a set of predictions that you can make by just doing some very simple analysis. And I'll show you that analysis in a second here. Okay, so that's the whole concept of scaling. You have a set of parameters, and you figure out how all the parameters vary, and then use that information to predict what's going to happen with area, power density, energy per operation, performance, clock frequency, and all those factors. Okay? Now, another thing that turns out that Dennard predicted, well, actually, it's not a prediction of Dennard. It's something that people have empirically figured out, is that the chips, while you're basically doubling the transistor density from generation to generation, we also make chips bigger from generation to generation. Actually, for a long time, it was true that if you go from one generation to the next one, every chip would get 14% larger. That's not true anymore. If I look at chips that are now being published at ISSCC conferences and things like that, and I compare them from the ones that were 3 years ago, and you look at the average size, it's approximately the same. Chip sizes have kind of fixed in size. And that's a good reason why, right? Suppose I keep on growing my microprocessor size, or my processor, or my mobile processor size. At some point in time, the chip becomes bigger than your cell phone. Right? That would not be a good idea either. So you're constrained by size factors. And cost factors, remember we talked also about the cost of yield things, that if you make chips bigger and bigger and bigger, the yield might go down as well, cost can go up, and so on and so forth. But for a long time, 14%. And then the last thing that you should be aware of is that the technology generation typically lasts about 2 to 3 years, which is fast, right? It means I plug down, I build a fab, let's say for 90 nanometers, and 3 years from now, I'm going to have to build a new fab for 65. And 3 years after that, you build a new fab for 45. And hopefully, you can still make some money off the old fabs, build older parts, right? You keep on running the 90 nanometer fabs for a while you already bring the new ones into action. Yes?
We are scaling down, so why did they increase the die size?
Well, it's more functionality. So you get double the number of transistors. And if I can make the die size larger, I get even more functionality. So that was the whole reasoning. That was always trying to cram more and more functions onto a chip, which was very important in the past, right? In the past, we were area limited. It was really the case, right? You say, there's so many things I can do, but there's only so much I can do on a given area of a chip. Today, the picture is a little bit different. People already kind of worried, oh, we have this 65 nanometer transistor chip up. So what are we going to do with it? I have 1 billion transistors. What the hell are we going to do with 1 billion transistors? Are we going to put 2 more processors down? Or whatever is the trade-off. So it's the fact that the area limitation that really was very stringent in the past is kind of gone away. We already integrate a complete system on a single die. You cannot do much better than that. In the past, you had to basically design, everything had to be 4 or 5 different parts on a board. Now everything is already on one chip. So why make them bigger? And then the cost factors start playing around as well. Now here's an interesting thing. This is from Gordon Moore himself. Gordon Moore basically had already predicted this kind of scaling of technology that would keep on going and so on and so forth. So he predicted that the transistors would double every 2-3 years. 18 months was his original number. Every 18 months, if you look at the original paper, we're going to double on transistors. He also predicted that wafer sizes would go bigger all the time. And he has given, that was a prediction in 75, he says, a wafer is going to go up with so much percent every year. So this was a talk he gave about 4 years ago at the ISSC conference as well. This is where I was wrong. If my wafer law would have basically continued, wafers today would be 57 inches, which means you would have silicon wafer you have to carry like that. Never happened. Today we're at what? 12 inches for a wafer. Some companies talking about 15-inch wafers. Maybe not. We'll see. But never going to be 57 inches, I think. That's a hell of a piece of silicon. To basically, you can actually put a plasma display on it, I guess. No, the plasma LCD display. You definitely would not do plasma. You can make it a big display. That's one thing you could do. So, but those numbers have been amazingly accurate. If you look back and you look at the minimum feature sizes and how they have scaled along the lines of what we said, basically this 2 times reduction in minimum feature size every 5 years, which is, you take it into account basically, which is your 18 months basically between technology generation, 18 months, 2 years, we see we're pretty amazingly accurate. Technology, the industry has followed their own roadmap very carefully. They extrapolate first, and then they follow their extrapolation. That's the way they do it. So, well, gee, we have to be at this node next time around, so they work really, really hard to get there. Same thing with transistor counts. If you look at transistor counts, have gone up substantially, have been from generation to generation, have gone up. And as I mentioned a couple of weeks ago at ISSC this year, Intel announced a chip with 2 billion transistors. It's quite staggering. So this is year 2000. We're sitting at around a couple of 100 million transistors. Now 2 billion transistors on a single die. A lot of it is memory, but still 2 billion transistors. Gate delay, as we predicted, linear scaling, well, exponential scaling. It's not linear, it's exponential. Every generation, delay goes down with a factor of 0.7. 0.7 next generation, 0.7 squared, 0.7 to the third. You put it on a log curve, and you can see your propagation delay going down and down. So we're now sitting, I think, over, let's see, if you look at 90 nanometers, typically inverter propagation delay is about, what is it, 8 picoseconds, 6 picoseconds, or something like that. So it's predicted that in a couple of generations, we might go down below a picosecond. I remember that we had to use basically liquid helium, superconductive devices to get to propagation delays of this type. That you had to put it really down to a couple of degrees Kelvin, and you have to use superconductive technologies to get to about a picosecond propagation delay. Just by scaling technology, we've gotten very close to those numbers today at room temperature, which is quite amazing. Power dissipation, if you look at the technology scaling, we see that it's going to go up. And I'm not going to go in more detail on this graph. It's fairly complex. There's a lot of factors in here. But what we've seen is that power dissipation is going up continuously. and power density is scaling up as well from generation to generation. It's still going up as we're speaking. Okay. Good. So now the question is, how do those guys make those models? Right? So how do they do that? Are they doing very sophisticated things? Not really. What they basically do is they take some simple equations and they put some scaling parameters in there, a number of independent parameters. So what happens if I scale the thickness of my oxide by so much, and the diffusion depth by so much, and the channel length by so much, and you put all this in an equation, and you come up with a fairly simple analytical model that basically predicts what's going to happen with your propagation delay capacitances, energy dissipation, and so on and so forth. Oops, missing this. Okay, so actually it turns out if you look at the Dennard model that I mentioned before, Dennard actually proposed this first model, which we call the full scaling model. It says the following thing. So we're going to scale technology with a factor S. And S, as I already mentioned, 0.7 typically from generation to generation. It says the ideal scaling, if I would scale things in an ideal fashion, what I would do is when I scale down the dimension, I'm going to make all the dimensions of my transistor smaller in the same way. So if I scale channel length, I'm also going to scale down the oxide thickness in the same way. I'm going to scale down diffusion. I'm going to scale all the dimensions in a similar way. Okay? Everything shrinks by the same ratio. Now, you can imagine if I do that while keeping my voltages basically constant, my supply voltage, what would happen is that the electrical field would keep on increasing. Right? From generation to generation, I scale down my dimensions while I keep the same voltages. Means my electrical field will go up by a factor of 0.7 approximately every generation. So you cannot do that. So the full scaling model assumes that you're not only scaling dimensions, but you also try to keep all the electrical field strengths the same while scaling as well. Okay, so I'm going to scale supply voltages and threshold voltages and all voltages in the same ratio as I scale the dimensions. Okay? That's what we call full scaling, or constant electrical field scaling. And you will see that if you do so, you're going to have to scale some other parameters. Right? If I basically start scaling down the dimension, I want to keep the electrical field, I'm also going to change doping levels, for instance. I'm going to have to increase the amount of doping levels in the substrate to maintain that. And that's what we've seen over the years, is that doping constants, substrate doping levels have gone up from generation to generation. So that was the full scaling model. That's the ideal model that we would like to stick with. And you can predict, again, what's going to happen with propagation delay and all those kind of things when I do so. Now, that's the ideal theory. Before that, however, before the 1990s, nobody cared about it. Actually, turned out that the industry was perfectly happy with the same supply voltage. Say, well, why don't we? They fixed the supply voltage 5 volt. It was a good number. TTL was 5 volt. So why not stick to 5 volt? It's a good round number. We have all our supplies sitting at 5 volt. The boards are designed, the interfaces are designed at 5 volts. So they stuck to 5 volts forever. So this is what we call fixed voltage scaling. You scale the dimensions, but you remain, all your voltages, supply voltage and threshold voltage remain constant. Now obviously, as a result of that, the electrical fields will basically go up. And you have to be very careful. So they did a whole bunch of tricks in the technology to make sure that you wouldn't get breakdown of some of the diode regions and so on and so forth, that you wouldn't get pushed through and all this kind of technology. By playing around very carefully with doping levels in the source and drain regions, in the channels, gate, and so on and so forth. They did a whole bunch of tricks to keep that 5 volt as a constant, till they basically couldn't stick to it any longer. Because the fact was that power dissipation, as we'll show you, it's nice when you keep supply voltages high. You might imagine, remember our analysis of propagation delay? Look at propagation delay, we see that higher voltages typically go faster. If you keep your voltages higher, you're going to go faster. So, hey, you get a lot of good performance. But you can imagine that if I put more and more transistors and I keep my supply voltage constant, my power is going to go up through the roof. So because I'm switching more and more devices faster and faster and faster, so power killed this guy off. So people started scaling the supply voltages as well. 5 volt, 3.3 volt. And then for a while it was actually quite simple. You look at your technology node and you know what the supply voltage is. If it's 180 nanometers, 1.8 volt. 130 nanometers, 1.3 volts. 90 nanometers should be 0.9 volt. You would expect now that for 65 nanometers we're going to go to 0.65 volt. Ain't going to happen. So we're actually now going back from full scaling. So for a while, so we were at fixed voltage scaling. Then we moved to full scaling for a while. And now we're moving back to fixed voltage scaling because we get stuck. We get stuck because of the fact that we cannot scale thresholds anymore. At 0.65 volt, you keep on scaling your thresholds lower and lower. Remember that leakage thingy? Your leakage goes through the roof and the power goes up again. So today we're kind of waffling. We're in waffle mode, basically. Nobody really knows what's going to happen with supply voltages in the years to come. Some people say they still have to scale. Other people say, no, we're not going to change them anymore. So that's the two extreme scaling models. Now, I can do something in between, which is the more realistic one. It says, well, I scale voltages and dimensions with different parameters. So are you going to use a parameter S for the technology or for the dimensions? I'm going to use a parameter U for the voltage scaling. Okay? So I have two parameters I can independently change. So if S is equal to U, then I get what? Full scaling. Right? If U is equal to 1, I get fixed voltage scaling. Okay? So you basically, by using that generalized modeling, scaling model, I can basically cover all the other cases as well by just choosing the relationship between S and U. Okay? Now, so that kind of summarizes a little bit. So this is what scaling does, right? So what I assume for full scaling is that all the dimensions in my transistor, if I go from one generation to the next one, I'm going to shrink everything exactly the same way. Okay? That basically means the length of the devices, the width of the devices, the junction depths of the devices, the drain regions, source regions, oxide thicknesses as well, another problem. I'm not going to talk too much about this, but you can imagine that you cannot keep on scaling oxide thicknesses too much. At some point in time, if you have only 3 atoms on top of each other, or 3 molecules on top of each other, scaling down is getting harder and harder. Right? You can go to 2, but then you have a sieve. You can go to 1, and you have no dielectric anymore, basically. Every electron kind of just walks through, and is perfectly happy. It's a conductor. So scaling of all these dimensions. Okay, so let's kind of now translate this into a scaling model. So this is the Dennard scaling model, full scaling. And let's assume for a while that initially we're going to assume that we have long channel devices. Big devices with a long channel. No velocity saturation yet. Okay? So the scaling model will say that all the dimensions in the full scaling, W, L, T, ox, all scale as 1 over S. Okay? So VDD and VT in the full scaling model also assume that both supply voltage and threshold voltage scale as the technology with the same factor S. Okay? So then we can easily compute all our derivative parameters. Like, for instance, area. Area of a transistor is W times L. Right? So we can see that if I scale W and L with a factor 1 over S, area will go down as 1 over S squared. Okay? That's my quadratic factor. Gate oxide, COX. What's happening from technology to technology generation? It's one of the reasons why our devices are getting faster from generation to generation. COX is equal to 1 over TOX. Right? Epsilon is proportional. This is not equal, this is proportional. It's epsilon ox, while epsilon ox is a constant over TOX. So TOX is shrinking. So the capacitance per unit area, gate capacitance, is actually going up from generation to generation. Because I make my oxide thinner, means that my capacitance is going to go up per unit area. However, my total gate capacitance, or let's assume, ignore the diffusion capacitance here. We assume that basically gate capacitance is the most important load capacitance. We say the load capacitance is Cox times W times L. So Cox goes up linearly from generation to generation, but at the same time, the area of the gate goes down quadratically. So what we see is that CL basically scales as 1 over S. Right? Well, depends on how, if it's smaller than 1 or larger than 1. Exactly, it scales like S if S is equal to 0.7. So we see that from generation to generation, the capacitance per gate or per inverter goes down linearly. Okay? It's a linear scaling as exactly equal to the technology. Now, if you look at the current, and I said this is a long channel device. Remember, long channel device, quadratic relationship between VGS and ID. So for my inverter, the saturation current that I'm having, the maximum current I'm getting out of a transistor is Cox times W over L times VDD minus VT squared. So you think about it, this goes down as S squared. The capacitance goes down as S. Let me just think about this for a second. W over L cancel out. What it says is that in this particular case, so this goes down and this goes up, so you get 1 over S times S squared, so you basically get S. What it says is that my current, the saturation current, scales down linearly from generation to generation. Okay? So if I put it all together, I can also compute R equivalent, which is VDD over ID sat, which I computed here. I can find also my equations for P average, and or the P average, the overall power dissipation of a single gate, or the power density. This is power density. Okay? And I can find all of those things as a function of S. And then it's quite trivial for me to build these nice complex tables that we discussed. This is what your technology roadmap basically looks like. It's more complex than that. They have more than one scaling parameter. But think about it, for instance, if I would do full scaling, which means I scale supply voltages in the same way as we scale basically the dimensions of the technology, we see that the propagation delay goes down with a factor S from generation to generation, just as we have shown happening in reality. Average power basically goes up per gate, goes down as a factor of S squared, and the power delay product, or the energy, goes down with a factor of S to the third. Now that's for full scaling. But if on the other hand I would have done fixed voltage scaling, where I keep the supply voltages and the thresholds constant as a function of, while I'm scaling the technology, we see that actually a very different picture emerges. We see that, the devices not only go actually faster, not by factor S, but a factor by S squared. That's why people like to stay at 5 volt in the past. You scale technology, and I get a squared type of improvement in performance. That's really cool. However, look at the power dissipation. The energy per gate, instead of scaling down as S to the third, actually is going 1 over S. Or you see that your power, or the energy per gate, you put more and more gates on the same contact, you see your power going up and up and up and up and up, and you run into barriers. That's why we went to this general scaling, where you put this as a function of S and U. Okay? But all of those things can be easily derived. Once you have your equations, you can just plug in the S values, the U values in your equation, and you can figure out how power density, average power, propagation delay, all those type of things evolve. Okay? So that's the whole idea of the scaling theory, scaling relationships. And it's kind of interesting. You might say, why do we talk about all this stuff? Right? Well, it's kind of interesting. It helps you to predict a little bit what would happen if I would go to the next technology generation. Helps you to figure out, gee, I want to, sometimes you can make a choice, right? I have a processor for a given function. Let's say I want to put a TV receiver in this thing here. I want to watch TV on the thing. So what's the better thing for me to do? Well, it takes, the current version takes me, let's say, 1 watt of power. What's better? Should I spend a lot of time of making my design better? Right? Take a bunch of designers and make them work really hard to reduce the power dissipation of that thing? Or should I just say, well, no, I'm just going to move to the next technology generation, and I get it for free. Well, not for free. You have to build a fab and all this kind of stuff. But I just get it as a result of the technology scaling. I don't really have to do any redesign. So this is kind of the predictions you can make by looking at this type of tables here. And this is for long channel devices. We can easily do this also for short channel devices. And there's only one major difference. The major difference here is that the saturation current is not quadratic with the voltage anymore, but linear, as we discussed before. Okay? So, and you can come up with a similar table. This is the same table, but now for velocity saturated devices. And I'll definitely leave that as an exercise for you to kind of walk through that. So, this has been driving us for a very, very, very long time. And this is what the industry has been using forever, ages. It's a beautiful thing. The Dennard model basically has been kind of driving the industry for such a long period of time. However, what's happening right now is this kind of scaling theory thing, where you use some simple equations to predict where things might go, actually start to fail. And some companies got taken by surprise by that. They said, well, we're just going to keep on scaling, that I'm going to go to 65, and all this kind of goodies. Life is going to be beautiful. Life is going to be easy. We're going to be faster. We're going to have lower power. We're going to have cheaper, all the goodies together. Till they suddenly realized there was one thing that didn't scale as nicely as all the other ones. If you keep on scaling the supply voltages, turns out that this KT over Q thing, Boltzmann constant isn't something that scales with technology, unfortunately. The charge of an electron doesn't scale with technology. And I haven't known the temperature to change that much either. Global warming might change it a bit. Temperature might go up gradually, but a little bit, but it's not going to go down. I know that for sure. So KT over Q is a constant. And it turns out KT over Q basically sets our leakage current. So we have to set a certain VT. VT is a function of your KT over Q factor. There's only so much you can do. And we cannot scale VTs that much anymore as a result of this. So this has been a problem. Leakage has, we have scaled thresholds, but as a result of that, leakage has increased radically. And we have hit some cooling limits as a result of that. So today, we're kind of revisiting the model a little bit. Thresholds are staying constant. At least that's what's been predicted. Unless you come up with a beautiful new logic family, maybe it's part of your project, you can come up with something that kind of figures out how to get around this problem. But so far, I haven't seen anybody doing it so far. So we have a problem here, is that some of those scaling type of strategies that we've been using for such a long time starting to fail. And people are revisiting this whole model. And there might be new devices, right? There's a lot of nano stuff going on these days that might change this equation. It might go to a completely different scaling model. We don't know. And that's something we have to figure out. This is why this is a very exciting time. There's a whole bunch of new stuff bubbling. But the one thing is for sure, the old stuff kind of slowly but surely kind of grinds towards some limitations. And we're going to have to do some new things if we want to keep on doing more functionality for a smaller cost. Okay? So that's it for today. So we have one more lecture tomorrow, this week, which is going to be about complex logic. So we're going to talk a little bit about taking what we've done for inverters. And now we're going to start talking about NAND gates, NOR gates, and all kind of other goodies. So we can make something a little bit more complex. Okay? See you tomorrow. So I saw your email. Yeah. So you add some, move the curve a little bit. Yeah, I'm going to play around. I might remove the last part of the question, but I'm not sure.
Which one was the last part?
The